recording. So we were repeating the last week's course material and warming up. Sağ ol Hamza. Hamza Mahmut. Okay. I'm sorry. Bir dakika sesi kapatmak zorundayım. Zaman zaman sesi kapatacağım, böyle nahoş sesler duymanızı istemiyorum. Sadece dersle ilgili sesleri duyun. Hastayım çünkü. Evet, devam ediyoruz. Şeyimizi kaybetmiyoruz, gücümüzü kaybetmiyoruz. Haydi bakalım. So this is the second order system, and we have seen that the roots are changing their locations from actual pole values. S equal nerede bu? Pole values. S equals 0, S equal -2. Journey is starting from those values. You can see S equals 0, S equal -2. Then it's going to come here and increase. That curve might satisfy us, and we can select whatever the K value we would have, and we would be very happy. That's possible. For example, at this point, you have a good step response for K equal K1 here. System is always stable since the roots are always in the left-hand side of the S-plane. S-plane, however, that one has got one pole equals 0, the other one is -1, the other one is -2. So we have three poles. When you draw the three poles curve, I have several times repeated that one. So I'm just going to increase that one. The root locus curve is going to draw that curve. So you can see that it's not far away from origin, and also you have, while you are changing the K value, you might have unstable region as well. Be careful. So you are not free to increase K as high as possible. And this value seems to be appropriate, 60 degree. 60 degree is zeta's 0.5. Your examination question, you remember that? In your examination question, you have zeta was 60 degree, or zeta was 0.5. Anyway, so however, the third root, since there is no zero, if there would have been zeros here, the journey is going to end up with zeros, but it is not. We haven't got any. Therefore, it's going to be asymptotic. One of the curve is moving in this direction, and the other one is moving in that direction, the other one, while increasing the K. Okay. But it's giving us a very good idea what's going on here. This example, that example has got 1 0 here, and zero effect, I'm going to discuss it with you. Zero always tries to pull the curves to the left hand side, so it's nice actually. So it draws the curve to it takes away from the unstable part. Okay, but when you write the root locus MATLAB program, it's going to immediately draw that one, starting from that pole and this pole, K equals 0 values, and then moving like this. Of course, we can select any point here, but that seems to be that 0.7, zeta equal 0.7 is nice for this example. For that example, we have 1, 2, 3, 4. 4 poles, 1, 0. 4 poles, 1, 0. All you have to do to write the GH and then or obtain the transfer function, write the transfer function. And numden, then root locus numden. Or root locus system. If you define the system, then you should say system. Just a moment. If you have a lot of poles like this, you are going to concentrate on the dominant poles. These are dominant poles, for example. That one is dominant. However, of course, we have one pole here, one pole there, k equals 0, one pole here, one pole there, and there are two curves. This is what root locus is all about. I'm going to repeat those in the next slide anyway. So that's okay. That's what I repeated. Okay. Now we are going to jump to the original starting point. Again, I repeat those equations and the curves. We spend only 10 more or 15 more minutes to warm up. This is what I believe. My teaching method is such that every student should warm up, then continue to the next chapter. Evet. Ninth chapter or ninth week. I'm going to put that one in your all-learn system as well. It's a continuation of the one before. I continue, and I just let us remember what we have learned last week. We did that, so I'm going to be moving a little bit fast. So this is the, follow my cursor please. This is your characteristic equation, and we know that characteristic equation should be equal to 0. That means GSHS should be -1. Amplitude of this one should be 1, and the angle should be 180 degree. Those angle is going to be important while we are learning compensation methods. That's what I omitted in the first course, so I'm going to concentrate a bit. That's only one real pole, and the curve is like this. That means while you are increasing your k, your roots are going to locate it for each k value, but it's always a real. There's no oscillation, nothing at all. Or origin, of course, starting origin. This is starting from -1 over t1 or tau1. Tau is a time constant here. This tau, I generally use tau. Probably next year you are going to be my student in power electronics course as well. Tau is a time constant, but some books use T. T, that one. Bakalım yazıda bir sıkıntı çıkmayacak inşallah. T actually, I don't want to use, but for example, Professor Ogata's book, which I'm following, using time constant. This one is time constant for Ogata. For Ogata, it's a time constant. That one tau, o da time constant. O Hooft, bunlar dünyanın en meşhur iki kitabı. Hooft and Bishop. Bishops. Both books are called Advanced Control Systems. The names are almost the same. Sorry about that. Beni okulda görenler bilir. Those who see me in university, I always use mask. However, I captured. I don't know. It's not corona, by the way. However, it's something not very good. Capturing, I've got flu, they call it, but it's a virus anyway. Okay, so these are, temizleyelim burayı. These are time constants. That one, 1 over time constant minus value is a pole. However, for second order system, these are, we have one pole is located here, the other pole is located here. So in between those, a parallel line. Or if one pole is located in zero, as you can see, kursörü kaybetmişim. As you can see my cursor, one pole is located at zero, the other pole is located in minus 1 over tau. Then those in between, the curves, the value of poles are changing its value while you are increasing the k. Of course, you can, for example, that's nice point. That one is a nice point, 60 degree, 45 degree. You know, those angles are nice. However, if you add another pole here, and then you are going to see that the location of the poles are moving towards unstable region. So you have to be careful. By if you know the equation like this, you can of course always use Routh-Hurwitz criterion on stability. Therefore, you can obtain the value at which k the system is going to be unstable. But computer itself is also telling you. If you put your cursor in that point, it's going to give you the value of k here. Anyway, if you have a poles like this, it's a bit far away. Not far away, but it's a little bit away from origin. That one pole is located here. So these two poles are composing the waveform like this. That one, which is away from origin, it's a single one, and of course this pole also is moving while you are increasing. I would prefer, for example, this point. I would prefer this point, for example, or this one. Probably it might have been somewhere there. Yeah, that's right. For this one, I wouldn't like that one, for example. I would prefer this value of k. 45 degree, between 45 degrees, 60 degree, depends how much overshoot you are allowed, how much, how fast your system should be. If you remember, I don't know whether you remember or not, since I'm not very happy about your examination papers, by the way. Ts was equal to 3 over sigma or 4 over sigma, depending upon the 2% rule or 5%. This is 5% rule. So result, the output so at the end, if it is the difference between steady state value origin 5%, of course it's better, then time is lower, but for that one, time is longer, 2%. One of them, but one thing is important. Who is going to tell me which one is important here? Which one is important? In order to reduce the settling time, you have to increase your sigma. What is your sigma, by the way? Your pole S12 is equal to minus sigma plus m minus omega d. Omega d here, for example, şurada göstereyim. That one is omega d, but this one is sigma. So if it is far away from origin, it's nice. The steady state, the settling time is going to be better. Higher the sigma, the real part of the pole. For example, that one, sigma is lower. And a lot of oscillation occurs here. Sorry, I couldn't show the. For example, for that pole, it's not very good. A lot of oscillation occurs, plus settling time is longer. However, that one is not very good since system also affected that one. We expect some kind of solutions like this. These are the best points. Anyway, this is not my today's topic. However, we are discussing those curves. If you have 1, 0, 1, 2, 3 poles, so you can see the effect of 0. 0 for the early one, we have 3 poles. You can see that 3 poles we have. The curve is like this. But if you put a 0 somewhere, you can see that curve is away from origin. So curve is becoming something like this. One pole is there, the other pole is there. These 2 poles provide a waveform, this waveform. However, that pole here is moving towards the 0, since we know that the journey is going to start from poles and end up with zeros. Since there is no enough zeros in our system, these are asymptotic values. Those curves are asymptotic. But that one is end up with this one. For k equal infinite, for example, for k equal infinite, zero, and that one. That one here is infinite. So it's moving in like this. The other are the other curves, poles are moving like this. Anyway, but if you have a zero, but if you have one of the poles which are double origin, double poles, S square, of course curve, temizleyelim bir, ondan sonra bir daha discuss edelim. So you can see that while one of the pole here, the other pole is there, of course, it's a little bit away from origin. But here, it's starting from origin. It's always stable, but it's not very good, that one. And of course, if you have two poles are located origin, then it's going to be oscillating. You know, if the transfer function is located in roots of the transfer function located on the j omega line, we have proved that it's oscillating. So it's a cosine or sine function. However, this is worse than that. Three poles are located at origin. Of course, it's always unstable. Two poles are in the right-hand side, so system is unstable. This one is also unstable too. So two roots are in the right-hand side. We have two poles are located origin. One of the pole is located somewhere minus 1/tau, but that's not very good. Even adding a zero here is not providing stable solution here. You can see that. Anyway, what we have learned, the learned we have got is that we can draw root locus curve no matter how complex your transfer function would be. Just write num, then step num, then you can see step responses, ramp. You can get the ramp response or impulse response, or you can draw the root locus curve. Okay. So I continue. And also, for example, that one is interesting. For zero value of k is terrible, and for small values of k is still terrible since the roots are in the right hand side. But for a certain value of k, higher value of k, system becomes stable. Since you added two, you can see that it was s square'e geri dönüyorum. S square mi? S power to 3 mi? Ya triple power. Triple power'a bir geri dönüyorum çocuklar. Hangisiydi triple power? Şuydu galiba. Bakayım bir dakika büyütelim. Evet bu. Now, what are we going to do if you have a system like this? It's unstable. All you have to do to add two zeros. You can see that if you add two zeros here and the increase k value, then you end up with those values. For example, it's a nice value, that one. That pole is nice. And that pole, of course, symmetrical is going to be provided. Or you can prefer that pole as well. But in the meantime, also, there is a risk here, since one pole is located here, and it's moving to zero. So the journey ends up with zero here, and this end up with zero here, and the curve, one of them is moving like this, the other one is coming to 0 point. These are zeros. Zeroları başka bir renkle göstereceğim. Bunlar çünkü pole dedik bunlara. Kırmızılara pole dedik. 3 tane pol var. Evet. Eflatun net görünüyor. Zero'lardan biri bu. Diğeri bu. So journey ends up in there. So one direction is moving in this direction, is coming here and going there. The other one is moving. But however, we have 3 poles. One pole is located here and then moving to this one. Hemen compare edelim bunu. Bakın burada 1, 2, 3. So I'm sorry. 1, 2, 3, 4. 2 poles double in origin and another 2 poles are located and the curve is, and adding 1 0, the curve is going to be something like this. Çocuklar, you might cancel, bunu ileride anlatacağım nasıl olsa. Atlıyorum burayı. Yeah, if you write this differential equation or this transfer function here, you can see that S plus this is GS, by the way, GS. So you have 1 0 another, sorry, bunlar pole. Şurada bir bölü işareti var. S equals 0 pole, S minus 0.5 bir tane, bir de 2 tane yerini bilmediğim şeyler var. O yerini bilmediklerimi hemen söyleyeyim. Biri, polları kırmızıyla gösteriyordum. Devam edeceğim ona. Bir tanesi burada. The other one da burada. Symmetrical, of course. Başka neredeydi? Zaten buradan yapmışız bak. S1 is 0. S2 is 0.5. Bir tane burada, şurada var. Bir tane de, I'm sorry. Böyle şeye basılı tutunca hemen yazı veriyor. Ben en iyisi kalemle yazayım. One of them is here, the other one is there. Of course, curve is leaving the stable point. Origin, you can see 0 here. So 0 can be seen here. So it's really not very good curve, that one. Yeah, we are not happy about this one. The book shows that if you want, you can also plot the points. So if the number of poles are, the difference between those is very narrow, that means, for example, here you can see that for this part, no matter whether you increase the K, is your system is not moving much. But for those K values, of course, you are going to obtain for different adjacent K values, you are going to obtain wider pole values. I'm not sure whether you understand that one or not. Just a moment. These are the curves. These are continuous curves, okay? However, that means you are actually getting K 0.001, 0.002, 0.003, then 0.11, 0.12. So you are getting infinite number of Ks, and those curves are driven. However, in order to see the change in the K, the effect of the change of the K, you can also draw those curves. There are statements. I don't remember actually now the statement of this one, but if you look at the you can learn how to write those curves as well. Kitapta vardır da şimdi zaman harcamayayım onunla. Evet. State space, I'm not emphasizing state space. However, without mentioning it, it would be, it is necessary to mention it anyway. For, you remember state space equations, ax plus bu is equal x double dot. X dot, derivation of x is equal ax plus bu. And also output y is equal c times x plus d times x plus d times u. That's right. Buradan baktım söyledim. Evet. Şimdi bunu bakın çok basit. Yani hani sorumlu olmayacaksınız ama bilmenizde yarar var. If you write, yazmamışız. If you write num a, b, c, d, just a moment. Bakayım statement var mı onunla ilgili? Olması lazım. Evet. Yazıyorum buraya. Sizde de bulunsun. Kaç kalınlık? 3 punto iyi. A space minus 56. Şunu yazıyoruz. Son satır. Minus 56. Space kaç yazayım? Minus 14. Minus 14. Kapat bunu. Don't forget to put comma here. B'yi de similarly B'yi yazarsınız. Similarly C'yi yazarsınız. And similarly D'yi yazarsınız. D mesela basit. D'ye hemen eşittir 0 yazabilirsiniz. Sonra noktalı virgül, noktalı virgül, noktalı virgül. Bunları yazdıktan sonra K equal sıfırdan başlamak üzere 0 2 nokta üst üste point 1 stepleri bu. Point 1 step to 400. 0 birden 400'e kadar değişiyor. It's changing from point 1 to 400. Then all you have to do root locus, esas yazacağınız bu. Root locus A, B, C, virgül var aralarında, unutmayın. Ben unuttum. C, D and K yazdığınızda bir de şey çizmiş ama onu boş ver. Grid mrid falan var. Sınır çizmiş. Bunu yazdığınızda bu çıkar. Ne çıkar? Bu çıkar. Root locus plot of the system defined in state space when A, B, C, D are given. Okay. This is the curve you obtain. Bu ne öğretti bize? It tells us that for K equals 0, I'm sorry, yes, K equals 0, we have here one point here. Biraz büyüteyim de gözümde görsün iyi. İyi ki de görmüş. For K equals 0, one pole is located here. You can see. So the trajectory is moving towards 0. And also the other two poles are moving up here. So that means you are going to obtain also, if you write step num, then you are going to get step response or ramp response as well. That is what's the transfer function of this one, or GH? What's that one here? Can you write this one to me? If num is equal 1 and then şimdi bu ne bu? Bu sayı, number. Bu s. Bu s square. Bu s to power 3. S küp, sorry, s to power 3 plus 4s square plus 5s, ondan sonra başka bir şey yok. Böyle bir grafiğiniz varsa eğer, şimdi bir şey öğretiyor bize çocuklar bu grafikler. Bakın. Zeta constant curves, büyütüyorum. These are zeta constant curves. So you can draw zeta constant curves, and if you have, for example, you remember that we have bir dakika olmadı. For the third order system, you remember that we used to have one pole here, the other pole is there, and bir tane de uzakta var. Şimdi bu böyle K equal sonsuza gidiyor. Goes to K equal 5. But that one is also K equal infinite. That one also K equal infinite. So if you draw zeta lines, you can decide which zeta you are going to obtain. For example, 7 bayağı iyi bir değer. 60 derece bakın. Şu güzel. Buradan da 7. Nerede o? Heh. Omega n de çizebilirsiniz. Omega n zeta constant curves. For example here, for this example, biraz küçülteceğim şimdi. Bu büyük çizilmiş nasıl olsa. Plot zeta 0.5 and 0.7 lines and omega n 0.5, 1 and 2. Of course, omega n, you remember that, şurayı büyüteyim iyice bakın çocuklar. Artık buralar yani yerli yerine otursun, bir daha yani tereddüt almasın kafanızda. Ben imtihanda onun için sordum. Yani çizsinler, yerine baksınlar. Bakın. Polun biri burada diyelim. Diğeri de aşağıda. One of the pole is located here. Bu ne bu? Bu şu uzunluk omega n. For imaginary part omega d. For the real part burada göstermemiş. Sigma. Of course minus negatif tarafta. Sigma. Şimdi dolayısıyla bu da öbür pol. Simetrik çıkar çünkü. S12 S12 is equal minus sigma plus and minus C omega d çıkar. Ama omega n'leri ben bilmek istiyorsam omega n'in geometrik yeri can be seen from this part. You can see one of them. That one here. Omega n1 curve. That one here is a omega equal 0.5 curve. And also you can see that omega 2 curve. Now we can see that from this part, we can see that in our MATLAB curves, we can see our zeta curves as well as omega n curves as well. And you can be sure that, of course, you can see step then or ramp curve and things like this. You can see the responses, whether those are satisfactory or not. And also, the steady state error is important too. That one, for example, is another interesting example. You have, ben de misiniz bilmiyorum. Are you with me? You have two zeros. You can see that two zeros and 1, 2, 3, 4, 5. 5 poles. Şimdi bir quiz açacağım çocuklar. Ben de olup olmadığınızı anlayacağım. Yet. Okay. Bir arkadaşınız soruyor. Diyor ki how many zeros, how many poles? Bir daha bak. Şimdi burada şu işarete yani tabii çok biraz büyüteyim iyicene. Görüyor musunuz? Şimdi burada bu GS'in işareti. Şurada da bir bölme işareti var. Burada bir bölme işareti var. Bunlar zerolar. Bunlar da poles. Şimdi burada kaç pol var? 1. 1. Minus 4, 2. Minus 6, 3, 3. And also we have two poles here. 1, 2, 3, 4, 5. 5 tane pol var burada. 1, 2, 3, 4, 5. We have 5 poles here and 2 zeros here. Tamam mı? Şimdi ben anket açacaktım size. Buradan kopya çekerek açacağım. Evet, açtım şeyi. Burada resim görünüyor. Zero'ları soruyorum. Tamam mı? Zeros are approximately minus 0.7 and J minus 0.7. Approximately that one diyorum. Doğru mu yanlış mı? Is it correct or not? İki tane zero vardı biliyorsunuz. Evet, oy vermeye başlayabilirsiniz. Kör burada. Biraz oynatayım yerini. Siz de görün. Zero'lar, pollar görünüyor bakın. Hadi sadece 6 kişi cevap verdi. We only have 6 students. What about the Other 6 students. Come on. Daha fazla beklemeyeceğim çocuklar. 1-2 dakika daha bekleyeceğim. Bir dakika daha doğrusu. Sonra cevaba geçeceğim. Evet, 8 kişi cevap verdi. 4 kişiden cevap yok. Kapatıyorum artık. Evet. 5 kişi yes dedi galiba. 4 kişi no dedi. Efendim Adel. Ne demek there is only one and two Adel? I don't see yes or no. Bir dakika ya. Cevap. Ha. Bir yes olsun, iki no olsun. Hay Allah. İlk yanıt seçeneği yes. İkinci yanıt seçeneği no. Yok. Ha, şimdi oldu. Baştan. Doğru mu değil mi? Haydi çabuk olun. Çabuk. Zaten atmıştınız oy. Hadi 7 kişi verdi oy. 6 kişi bekliyor. Come on, hurry up. We have 5 students left. 4. Diğerleri sınıfta değil mi acaba? Yoksa. What about the others? That those 4 people couldn't answer. Okay, kapatıyorum artık. 9 students already answered. We have 12 students in our classroom. Can you see the result? 6 students said yes, 3 students said no. Tamam, görebiliyorsunuz. Tamam, anladım, görüyorsunuz. Peki, şimdi bunu kapatıyorum. Bu 6 tane evet diyene soracağım. Burada hangisi zero, hangisi Paul? That is zero. Bakın denklem de burada yukarıda. These are the zeros. You might solve this one as well, but computer itself solved. And zero is here. Yani the real part is one, değil mi? 1 minus 1. But imaginary part is 1.7 or something like this. So these are the one I gave you. I gave you those poles actually. I deliberately try to understand whether you are differentiate the poles and zeros. It seems that you cannot. So you have to concentrate on that one. Okay. I'm going to take a break. Saatim benim geçiyor, 5 geçiyor. 15 dakikası 15 bir dakika. 10 17. Tamam mı? Yani ama 17'de tam gelin ha. Tamam mı? Okay. See you then. Hello again. I'm sorry. Evet. Evet. Burada bu problem basit bir problem. It was a simple problem. I asked you. So you can see that the journey is starting actually from this point and then moving unstable region for between k equal 12 and 73 it's unstable. Between 73 154 is stable, and then again unstable. This is not a very good one, by the way. On the other hand, that pole and this pole are moving like this and then end up with this point at this 1 0 and the other 0 here. So you can easily detect after the probably the quiz. You can now improve your selecting 0 pole capabilities. That is the example. You have 1 0 here. Let's read the material first. I'm sorry. Let's read the material first. If all zeros and poles of a system lie in the left-hand plane, bütün pole'lar, all the poles and zeros are in the left-hand plane, then this system is called minimum phase system. If the system has some poles or zeros are in the right-hand side, it's called non-minimum phase. This minimum phase and non-minimum phase probably is going to be used in the frequency response of the system, which now it's not very important. However, if you look at that curve, for example, Rootlacus curve is this one. So starting from 0, one of them is 0. The other one is minus 1 over t. You can see that. T here is a time constant, by the way. And then moving like this, coming here, and then moving. And for a certain value of that one, which becomes beyond that unstable. So this is the limit. I checked that one. I solved this transfer function and then write the Raut-Hurwitz equation, and I have seen that that is the point which represent the limit of the stability. You cannot increase your k higher than this value. This is k0 value, this is k0 value, but this one is k infinite value. So the curve is moving like this. The other curve is coming here as well. One of them is moving away, the other one is coming down. Okay, since we haven't got two zeros here, so we all know that the journey is going to stop at zeros. If there isn't enough zeros available, which is the case normally, then of course some curves are going to be asymptotic. That one, for example. Anladınız mı bilmiyorum. Tekrar edeyim. Rootlacus is also telling us whether the curve is in the right hand side or not, and then it's telling us by looking at that curves you can see whether it's a minimum phase or non-minimum phase definition applied. Now the compensation of the root locus. In order to compensate the root locus, what we are doing actually, we are either have this one, biraz daha büyüteceğim. That one is our GC. So this is your main job. You are going to obtain, you are going to find what kind of function I should add into this system. You remember the examination question. I deliberately asked this, and you prefer to write the material, but you never interpret it. You never mentioned, only one or two person said that actually PID is the one you are adding two zeros and one pole, which is in origin. We are adding to the system. What PID is all about. Although some friends of yours missed even write the time domain equations. Of course, the derivation of the S domain equations are taken from the time domain equations. If you understand the time domain, then you can visualize the S domain results. Okay. Anyway, so you are going to design this GC, your job. It might be also that kind of curve as well. You might also add GC is in the feedback loop as well. It's seldom, not much, but this is also a possibility. Now we are going to see you already know that the effect of number of poles. One pole, two poles, three poles. So the effect is seen that if you increase the number of poles, curve intend to go to the right hand side. Okay, but adding zero is different. Adding zero is actually pulling the curve away from origin. Look, this is the classical curve. When you add a zero here, is pulling. Curve is now like this. It's asymptotic for k equal infinite. However, if you put a zero in front of the pole here, then it further takes the curve. So a system becomes stable. It's nice. Even if you put zero very near to origin, then it's even goes far away. One thing you should not forget that zero actually represents k equal infinite, but always coupled with the pole. So while you are increasing the k value, your points moving like this and come here. In the meantime, however, this pole and this pole are coupling, making a pair, and then curve is going to be something like this. So this zero actually is affecting those parts as well. That zero is even affecting further. So you can see that it makes a combination with that pole here, and then these two poles are free. Then all of a sudden, these two poles are organizing a good root locus curve. It's a nice one, good one. Now we are starting a new topic. So you have to be ready to learn actual compensation methods of root locus plots to be used for lead compensator. Okay. Now we are starting with lead compensator. This network is the output EOS over EIS is equal to, vermemişiz ama yazacağım şimdi. Ayrı bir temiz kağıda yazacağım çocuklar. Bunun transfer fonksiyonunu. Bir dakika. Output over input equal bir dakika. This is the transfer function. So you remember the op-amp circuits where R1, R2, R3 are defined. So you can see that R1, C1, follow my cursor please, R1, C1, R2, C2, and R3, R4 are defined like this. And here for lead network, R1, C1 is higher than R2, C2 lead network. And for that network, although I obtained transfer function, you are actually adding 1 0 and 1 pole to the system. I repeat, don't forget. You are actually for lead compensator, then you are going to learn the lag compensator as well. This is a lead compensator. You are adding 1 0 and 1 pole. If R1 C1 is higher than R2 C2, which I'm going to come back to that point while I'm going to write the equations, then I'm sorry, then of course it's a lead network. Lead network means that you are actually adding a system, a leading network. That means you are adding a system with a zero and pole, but zero is near to origin. Pole is far away, not far away, but away Logging. The pole lead means that this zero is in front anyway. But log network is opposite. Pole is you are adding a one pole and one zero, but pole is near to origin or in this part. That one, this zero is lagging. Okay. Zero. You also remember sinusoidal waveform, current waveform. Leading means that the current is leading, and the lagging means that current is lagging with respect to the original reference voltage. You remember that. I'm going to also emphasize that one during my power electronics course as well, lead and lag networks. But generally speaking, it is impedance, or if you are looking for current, then if impedance, your impedance for electric equivalent, I'm talking about. I'm not talking about this OPAM, operational amplifier network. For electric network, if impedance is biraz yazayım ya. Buraya yazı vereyim. Burada karışır. Tamam, kafanızı karıştırmayacağım. Hayır. Kontrola devam edeceğim. Elektrik circuit'ı sonra anlatırım. This NES network lead means that zero is near to the origin. Okay? And this one is lag. That one is lead. That one is lead. That one is lag. Okay? So we are adding a controller, lead controller here. I'm going to continue to derive the lead compensator equations. Okay. So output input relationship is something like this, and for lead R1 C1 is higher than R2 C2. So you can see R1 C1 here. You can see that, and R2 C2 here. So that means R1 C1 is higher, which if we write the equation again, which is equal to R4 C1 over R3 C2 So you can see that the final equation is this. Probably you are asking now, what is kg here and alpha here? Şimdi time constant t is equal R1 C1. Alpha is equal R2 C2 over R1 C1. O da eşittir. R1 C1 tau olduğuna göre R2 C2 over time constant. Kg here, that one here, R4 C1 over R3 C1. During my experience, which is over 40 years, I know that if you write those equations like this to your students, you are actually causing a lot of misunderstanding and confusing, and also you are not giving hope to your students to understand the topic. But I should give you hope to understand the topic. What's happening actually? This is your controller. This is your controller. GC, and that is the system. That is the output. Might be H here or not. H. So that actually this is the system. This is your wish, RS, but that is the reality, CS, output. But what we are now looking for, we are adding this system 1 0 and 1 pole. That's why I put this part this equation is important for me, since actually what I'm adding 1 0 and 1 pole. Şimdi I'm going to write that equation again. Buraya kadar ama I'm going to start from this one. The lead compensator operational amplifier equation solved, and it is obtained that it is R4 C1 R3 C2, which is Kg here, S plus 1 over R1 C1, S plus 1 over RC C2. In order to write those equations, you can of course if you define time constant is equal to R1 C1 here, so this becomes S plus 1 over T. On the other hand, that one become, I'm sorry, kürsörle çalışacağım bir daha. Baştan başlıyorum. I'm going to start from very beginning. So that is the transfer function of the operational amplifier. That is the one I am adding actually. That is GC. This is GC, that one. What I'm adding an amplitude and also 1 0 and 1 pole. However, I defined R1 C1 as a time constant, and also I defined alpha is equal to R2 C2 over R1 C1, which R1 C1 is higher than R2 C2. Be careful. Alpha is smaller than, kırmızıyla yazayım bunu, alpha is smaller than for lead compensator, alpha is smaller than 1. So this network we are going to add to our control system, like PID, like PID. But what we are doing actually, we are adding 1 0 and 1 pole. If alpha is smaller than 1, so if you look at that one, that becomes high and that becomes low. So low means near to origin, high means away from origin. That's why it's lead. You remember. So I'm going to come back to another clean page. Of course, these are S. In S domain, we are doing it. Alpha smaller than 1. So we are actually adding alpha is equal to R2 C2 over R1 C1. R1 C1 is equal to time constant, and Kc here is equal to R4 C1 over R3 C2. So these are the values, and that is our transfer function. Okay. And if you look at the location of the I'm sorry, just a moment, please. We are adding 1 0 here and 1 pole here. The pole is 1 over alpha t minus 1 over R2 C2 pole. 0 is minus 1 over R1 C1. So this is what we are doing actually. This is what lead compensator is all about. What is the benefit of it, by the way? In the meantime, those control books are also emphasizing we have two main concerns. One of them is our transient response should be acceptable, but also the second objective, steady state error should be as low as possible. For those you remember the steady state errors, we have discussed that one. I'm going to come back to anyway. First of all, I'm going to solve a problem for you. Bakayım şeyinize, slide'ınıza geri döneceğim. I'm going to come back to your original slide. Now, problem. This is a problem. GS I'm sorry, yeah, that's right. GS is equal to 10 over what's the difference? K is constant here. So you are not going to change it. You have a constant number here. So for that one, if you draw the root locus curve, you are going to obtain the pole. One of the pole is located here for 10, K equal 10. The other one is located here. Of course, journey is starting from 0 and minus 1, then moving like this. It's going to continue anyway if you increase K values, but for K equal 10, we are here. Are we happy about this? First, I ask this question to you. Transfer function nedir burada? TF is equal 10 over S plus 1. Yine başladı oynamaya. I'm sorry. Hepsini siliyorum. Bir daha yapacağım. TF is equal transfer function. Allah Allah. Transfer function is this. If you multiply with s over s plus 1, so you obtain the transfer function is equal to TF is equal to 10 over s square plus s plus 10. Now, how could you find this pole? If you solve s plus s square plus s plus 10, if you solve it, you are going to obtain that pole here, operational pole, and that that operational pole over there. Now I'm asking question to you. Are you happy with those poles? Who is going to answer? Are you happy? It's stable anyway. Sigma is minus 0.5. And omega d is equal to, uydurarak söylüyorum, plus and minus G3 something. Buradan bakarak söylüyorum. Aşağı yukarı G'den biraz büyük. 3 to 1. Bilmiyorum. I haven't solved this. When you solve that one, when you solve this one, you obtain those real and imaginary parts of the poles. And then you realize that your zeta is going to be cosinus beta. Maviyle çizeyim. Şu açı beta. Beta. Bilmiyorum kaç çıkar ama yani çok kötü çıkar. Kaç çıkar sizce? Yani tanjant, bir kere tanjant beta is equal to 3 bölü yani tanjant 6'ya bir bakın bakalım. Tanjant 6 kaç çıkıyor? Bir dakika. Yani uydurarak aldım 3'ü. Daha fazla hesabı uzatmasın diye. 3.1 falan herhalde orası. Hadi öyle alalım. Mavide miyiz? Kırmızı olsun. 3.1 alayım bunu. 3.2 belki, bilmiyorum. Şimdi tanjant beta equal 3.2 3.2 divided by 0.5 is equal to, şimdi bunun açısını bulacağız. Bir dakika. Bir dakika, bir yanlışlık var. Yanlış yaptım. Açı çok küçük çıktı. Tam tersi büyük çıkması lazımdı. Şuraya elle yapacağım. Tanjant beta is equal 3.1 over 0.5 eşittir. Kaç? 6 bir şey oluyor. Omega n is equal sigma square plus omega d square. Karekök. Neyse, şuna bir bakalım. Çocuklar, sizde hiç hesap makinesi falan yok mu? Yani sanki ben hesap yapmak zorundayım da siz oradan seyretmek durumundasınız gibi görünüyor. It looks as if I have to calculate I have to make the calculations and then you are going to enjoy yourself and listen. Why don't you calculate beta here? Tanjant beta bir daha yapacağım. 3.1 tabii art tanjant almadım. Yanlışlık orada oldu. 3.1 over 0.6 0.5 equal 6 point bir şey. Şimdi art tanjant alıp açıyı bulacağız. 80 derece, 81 derece. Beta yazıyorum buraya. Maviyle yazayım. Madem maviyle göstermişim betayı. Şimdi onun kosinüsünü alacağım. Maalesef 0.16 çıktı. Zeta şuraya yazıyorum. Zeta 0.16. 0.16 biz hiç memnun olacağımız bir grafik değil. İşte it's a very bad. Şimdi ne yapacağız çocuklar? Problemi kaybetmeyelim. We have, biraz küçültüyorum. We have a system like this and the value of k is approximately given 10, not approximately, it's 10 here. So we cannot play with it. And then your system has got a solution which zeta is 0.16, is terrible. And I'm going to show you now the waveform without any compensation. Of course, sigma also settling time. We'd better write the settling time as well. TS is equal 4 point sigma. Kaç yapıyor? 8 second yapıyor. This is what I obtained. I'm not happy. It takes 8 seconds to settle down the waveform, and also it has incredible overshoot. Probably 60 falan çıkacaktır. Bakacağız şimdi. Geri dönüyorum orijinal curve'e. Problemi anladık mı çocuklar? Biz bundan we are not happy about this. We are not happy. What are we going to do? We are going to use lead compensator to make much better. But how unhappy we are going to see the that's right. Uncompensated curve. Yaptığım hesap doğru mu ona da bakacağız şimdi. Burası 5 saniye. That scale here is 5 seconds. So probably my calculation is correct. I obtained that it's 8 seconds settling time, and overshoot is 60%. You can see that we have 60% overshoot. This is a step response, uncompensated. That curve is uncompensated. It's a terrible curve. We are not happy. Tamam mı? Tamam. Now what we are going to do, we are going to use a lead compensator. There are two methods. One of them is depending upon a lot of angle calculations and things like this. I'm not happy about that one. So I'm going to omit this one. But what we would like to see now, by adding GC here, we would like to have zeta. This is desired. You can see that desired pole. That's the desired pole. And we prefer sigma is equal minus 1.5 and omega d is equal to this one. So we prefer the final S12 should be minus 1.5. We have to reach that point, plus and minus J 2.5. And omega here, omega n is going to be 3. And also angle beta is equal to 60 degree. We all know that zeta is 0.5. Is nice, objective. How could I object that one? How could I locate my pole here? Of course, the symmetrical one is also located there. How could I shift those poles since I have, unfortunately, that curve here? So these are the poles. I would like to get rid of those poles. There are methods, but what I'm proposing, if you read the book, you can see that the first method and the second method. I am going to propose you the second method. It's easier to understand. It's easier to implement. We are going to add a 0 to this system and pole. That adding 0 is somewhere there canceling this pole. So if we add a 0 here, so with what we are going to do, ben gene clean page'e gideyim. Ya da bu da güzelmiş. Bunun üzerinde yapacağım şimdi. Bundan hep memnun değiliz, tamam mı? Şimdi buna bir temizleyelim burayı. Nereye gitmek istiyoruz biz? We would like to find kaçtı? Yazmadım da ama 2,5'tu galiba şey. Evet. Bu 2,5'tu. Öbürü de hay Allah. Teta değil. Umduğumuz curve. Burada. Doğru söylemişsin. 1,5 eksi 1,5 demiş arkadaşınız. Ben teta anladım onu. Veyahut da beta anladım. Eksi 1,5'a 2.6. 2.6 değil mi o? Yanlış görmüyorum. Bir dakika biraz daha büyütelim. Tabii 2.6. Şimdi not alıyorum buraya. Eksi 1.5, eksi 1.5, 2.6. Artı eksi G 2.6. Şimdi tekrar dönüyorum istenilen grafiğe. Şu mutsuz olduğumuz grafiğe. Şimdi bunun üzerine işaretleyeceğim çocuklar. Ne istiyorduk biz? 2.6 istiyorduk. Öbürü de 1.5 istiyorduk. Demek ki bir tanesi şurası sigma, hadi. Sorry about Turkish. What we would like to have 1.5 here. Minus 1.5. And also this one is 2.6. That one is 2.6 here. So poles are, roughly speaking, are going to be located here. These are, cezanı vermesin. Nasıl küçülüyor ya böyle. Zaten bunu güzel çizememişim. The other pole is located there. Okay. O da olmadı. Ona yanlış işaretledim. O kadar da değil. The other pole is somewhere there. 1.5. Tamam. Şimdi now, but however we have a pole here. We would like to get rid of the pole. What I'm going to add 1, 0 here. The angle here, that one. Çocuklar bu hiç izin vermiyor bana ya. Bu ne yapıyor bu böyle ya? You remember this angle 120 degree. Değil mi? Bu, that one pole is located here 0. And now we are going to add a 0 here to cancel this pole. However, we have to, so we are going to add a 0 here. However, we are going to add a pole somewhere there. So if you add a pole here, o add'leri başka renk göstereceğim çocuklar. Vazgeçtim. Additional'ları başka renk göstereceğim. Bunları çünkü şey yaptık. I'm going to show it in different color. Those who cannot understand Turkish means that what I'm saying, some, I'm going to do that, I'm going to do this, is not relevant to our course. I said I would like to change the color. I said. So the violet color is the one we add 1, 0 here. Okay, and also we add one pole is here. This is lead compensator values. This pole's angle is rather important, since that one is 120. If we add 60 degree here, if I add 60 degree here, it's going to be total 180 degrees. So this pole and that zero together is going to, you see, the condition should be, the amplitude should be 1 plus GH amplitude, or GH amplitude should be -1, or amplitude should be 1, and the angle should be 180 degree, and the odd order of those. Now, what I'm doing, I'm not happy. I'm not happy about that one, which I have proved that how unhappy I am. 60% overshoot, 8 seconds settling time. We can't be happy about this. So we select some poles which we might be happy about those poles, but in order to obtain those poles, we have to get rid of those poles. We have to get rid of. In order to get rid of that one, I'm going to add a 0 here. All right, 1 0 I'm adding, and also one pole which is going to satisfy. If I put a pole here, -3 is satisfying the result. Evet, zaten şeyi çözmüş. Kitabınız bu 3 nokta polları vermiş. Yani burada geçen ders konuştuğumuz, yani geçen ders derken bundan önce konuştuğumuz neden ANP olmadığımız sırasında polun bir tanesi işte real part was -0.5, the other one is J 3.1. So zeta is hesapladık zaten biz 15 ve omega n de onu hesaplamamıştım. O da işte aşağı is approximately 3. Şimdi now we are going to add a lead compensator here. Lead compensator means we are adding that's the one we are going to add. Now, all we have to do to calculate alpha and t. We would like to obtain alpha and t values. The second method I'm going to propose, okay? So what I'm adding here, GC is equal to KC times. Şimdi bunu siz yazdırın bana çocuklar. Ne yazayım buraya? Bu kaçtı bu nokta? Bu nokta kaçtı? Evet, buraya eklemeyelim. Bu noktayı buraya eklemeyelim. Şu polu def edelim başımızdan. Bunu siliyorum. Bir dakika. Bunu siliyorum. Bunun tepesine koyacağız. Ki ondan kurtulalım. Bunun tepesine bir zero koyuyoruz. Nerede o? Heh. Bundan kurtuluyoruz. Buna bir zero koyarsak bundan kurtuluruz. Değil mi? Şimdi bundan kurtulma diye bir şey yok. Yanlış yaptım. Şu poldan bir başlangıçta kurtulmak lazım. Yani buraya bir S plus 1 ekleyeceğiz. S plus 1 minus buraya bir zero ekledik. Pol peki kaç olacak? İşte onu iyi bilmiyoruz. Çünkü henüz şeyi hesaplayamadık. Ha, o da eksi 3 diye karar vermiştik polda. Madem öyle onu da yazalım. S plus 3. Okay. Şimdi KC'yi hesaplamamız lazım. KC şimdi bir sorun var diyorum. Başta. Diyorum ki saat kaç? 11:20 geçiyor. 5 dakika 10 dakika ara vereceğim. 10 dakika sonra baştan alıp anlatacağım ve dört dörtlük öğreneceksiniz, tamam mı? 10 dakika ara veriyorum. Saat kaç şimdi? 21. Tamam. 11:31. 11:31. Break. Okay. See you. Hello again. Now I would like to understand the problem clearly and without any hesitation or any misunderstanding, fuzzy points remained. I don't want that one. The problem is this. It's obvious. If I ask you, that's the control system. This one is the follow my cursor, please. This one is the control system. And solve this system and obtain your step response. What you are going to obtain this curve. You are going to obtain this curve. While you are going to solve the system, you can obtain the zeta, you can obtain the poles, and you omega n, omega d, and then you can solve it, and you realize that it's going to be settling time. I have done it to you, the one before hour, 8 seconds necessary for settling time. Peak is 60%, is terrible. So we can't accept that one. What are we going to do? We are going to use second method of the compensation we are going to add here. And that compensation is going to be a lead compensator. General lead compensators are used if we are not happy about that kind of transient performance. I repeat, why someone may ask you why we use lead compensator is used if we are not happy about transient performance, settling time, the overshoots and things like this. And then we are not happy about this curve and that point, but instead we prefer zeta. For example, we select zeta, for example, 0.5. You know how zeta is affected to overshoot, so that means you are accepting that overshoot. And also you know how calculate the settling time. In order to reduce the settling time, we select minus 1.5. All right. Then, of course, this one is the required pole. We would like to reach that pole. If we do that, this is 120 degree. And also, we are going to add 1 0 and 1 pole. We know that it's a lead compensator. That means 0 is near to origin. But if I select the easiest way to select the 0 on top of the pole itself. So I'm actually canceling this pole here. S minus 1, I cancel it with by adding a 0 here. But in the meantime, you are going to add a pole here, of course, far away from origin. But of course, angle is important. If that one is 120 degree, this should be 60 degree. Okay. And then according to that one, it looks as if it said minus 3 is the added pole. So that is my controller I'm adding. 1 0, which is minus 1, 1 S is equal plus 3. Alpha kaç burada? Alpha is simple. Alpha, you can calculate alpha here. Bir dakika. 1 bölü T alfa 1 bölü T alfa eşittir 3. 3. 1 bölü T is equal 1. 1. Alpha is equal 1 over 3. Onu da yazalım buraya. Başka renge geçmek istiyorum artık. T here is 1 over T is 1, so T is equal to 1. Is obvious. Anyway, now for this new point, for this new operating point, while we are adding those 0, follow my cursor please, well, we are adding this 0 and this pole. So however, that point should satisfy our amplitude value as well. But we know that the total transfer function is equal to Kc times S plus 1 over S plus 3, that is Gc, times 10 over S plus 1. Amplitude should be 1. How could you reach that point? But for this value, the value here is S is equal to for S equal that point, the red one, minus 1.5 plus or minus plus diyelim 2.59 2.6 diyeyim ben kolayca. 2 nokta neyse çam çıkartmış kitabınız 5 9 8 J tabi var orada. J'yi unuttum. J. Bu değeri koyduğunuz zaman buraya S artı 1'ler götürüyor zaten. Devam ediyorum. Bir sonraki sayfaya geçeceğim artık. Zero'muzu nereye eklemiştik? Rengimizi alalım. Evet, bir zero şuraya ekledik. Bir zero buraya ekledik. Eksi 1'e. Minus 1'a. Bir de pol buraya ekledik. Bir de pol buraya ekledik. Ve GC'yi de hesapladık. Minus 0.5 plus G 2,98 diyelim, uzatmayalım. Bu eşittir 0.9 çıkar. Demek ki final value of controller GC GC is equal 0.9 times S plus 1 over S plus 3. So when you add this one, what's going to happen? Bir temiz sayfa açacağım ve problemi oraya taşıyacağım. Now system transfer function, artık rengimize dönelim. Blue. Evet. GC 5 punto çok kalın. Bir dakika. Puntayı küçültelim. Evet. GC yok artık. O kadar da değil. GCGS is equal to 0.9 times S plus 1 over S plus 3 times 10 over a new durum, new case, S plus 1. So that means your transfer function becomes 9, or sorry, your G becomes 9 over S plus 3. S plus 3. So your system becomes, the transfer function easily obtained is equal to 9 over S plus 3 over 1 plus 9 over S plus 3, which is equal to 9 over S square plus 3S plus 9. If you solve it, of course, S1, S2 is obtained. Minus 1 over, sorry, 1.5'dı. Ya da uzatmayayım bunu. Bunu zaten bulduk. S1, S2'yu buluruz buradan. Bir tanesini yazayım işte ise. Dur bakalım. S12 is equal minus 1.5 plus and minus J. Bu niye büyüyor ya? Ama 2.598. So step response, we all know what zeta is good. Look at slides, okay? For the value, generally comparing I'm reading from the book. Note that the present case, the zero of the lead compensator will cancel a pole of a plant, resulting in second order system rather than the third order system. We actually reduced the order. Actually, you can see the result here. As we designed using the static velocity error, by the way. Şimdi buraya başka bir renkle yazacağım bunu. Çünkü static velocity error konusunda çok üzerinde durmadık geçmişte. Static velocity error kv is equal limit s goes to 0 s GCS over GS. So we already happy about the transient, but we don't know how good your the velocity error constant is equal to limit s goes to 0. What about the function here? We can see that s which is equal to 3, which is equal to 3, is not really bad. So for this case, if you draw the curve, you can see that I come back. I'm sorry. The second method I teach you, the first method is the black one. The second method is the one I already teach you. This one here. You can see that. For example, settling time for this case. Bakın kaça düşmüş? Yani hemen yaparım buraya settling time'ı. Sigma'mız for the second method, sigma was, evet, violet color'la devam etmek istiyorum. Bu bizim grafiğimiz olsun. Şu grafik. Tamam. Şimdi TS, ne oluyor buna ya? Allah Allah. 3 bölü 1,5 2 second'a düştü. It was originally 8 second. Now it's 2 second. It's nice. Error also is reduced, and we obtain that curve. It's very good. As far as steady state error is concerned, the first method is rather better than us, but our method is very simple. You are just canceling one pole and then obtain kg. I'm going to give you a home assignment for this one. I'm not starting to lock compensator right now. It's already 5 past. I don't know whether Mohammed is already in the classroom or not. Yes. Seyit hocanız da gelmiş. Merhaba Seyit. Nasılsın?
Merhaba hocam, iyi misiniz? Nasılsınız?
Sağ olasın. Gördüğün gibi sesim fena değil ama düzeliyoruz yavaş
Geçmiş
yavaş.
hocam tekrardan.
Çocuklar yoklama alacağım şimdi. Son isim Yusuf Selim. Ondan evvel Yunus var, Reyd var, Omar var. Gidiyor yukarı doğru. Yani ilk isim de Abdurrahman. Kaybolmayın. Ben bu yoklamayı bir alayım. Seyit istersen bir 5 dakika ara ver onlara. Yani ben çünkü kaçta başladım? Buçukta mı başladım? Buçuğa 5:30'da başladım. Yani çok yorulmadılar aslında. Fazla şey yapma.
Tamam hocam, 5
Devam
dakika
edelim.
ara verelim.
Selam
Tamam.
hocam.
Bana mı soruyorsunuz?
Sir hocam, can I ask a little question?
Yes, please. Are you asking Nejat Tuncay or Seyit
I'm
Muhammed?
asking you hocam. Yeah.
Thank you. Okay.
Sir, I'm about makeup exam. Are we responsible for after midterm, topics or before, or just until the midterm?
No, whatever. I think I wrote a letter to you. You are responsible. You are not responsible for lead lag compensator and things like this, but you are responsible stability and other root locus curves and things like this. Okay?
Tamam. Okay. Have a nice day.
Efendim. Omar söyle. Omar. Omar, as I told you, you are responsible you are not responsible for lead compensator, log compensators. I taught today, but you are also responsible the root locus as well. Okay.
Hello everybody, we're gonna start the lab now. Does everyone hear? Assume you're here, let's start the lab. Okay, let's start with, today we're gonna do something in simulating. Today we're gonna take a look at steady state error and we're gonna analyze the step input and ramp input. First, let's create a system for, okay, let me share my screen first. All right. Okay, so let's create a system first. We need a step input. Let's start with step input first. And then we need a transfer function. We just write transfer function here. And then we're gonna add a sum. And then we need a scope for observe the output. And then we need a mux block for the inputs. Okay, let's say we have a step input here. All right, step input goes to our sum. Okay, now our sum, we're gonna determine a feedback. Let's connect our sum to the transfer function. Our transfer function one goes to mux, and then we're gonna connect the to scope to observe the output. Okay, let's say we're gonna determine our transfer function first. In here, there's your numerator and denominator coefficients, and you can just change it from here. Let's make it 2 here, all right? And here, 1 square, and we can change it to 2, and then you can apply it, and then you can set your transfer function. So here, now we're gonna do two things. So we have a feedback here, let's say, all right? For feedback, you connect sum to output of your transfer function. So feedback is negative, so you need to change your sum to negative, all right? Okay, now this is your feedback. In here, output of this sum is your error. Okay, you have a now step input here, and this is your feedback, and your input minus your feedback will be your error. So which means we have a we want a desired output in here, and our feedbacks give us in which position we are, all right? And let's directly connect our input to our output scope, so we can observe how the difference, how it changes with the feedback system, right? In here, in step function, you can change your signal value. We can change it to 50. Okay, now let's run our simulation and open our scope. Okay, now you can see the graph, right? So here the orange one is our input, our step input first. Now the second one is our output of our transfer function. Now first, as you can see, when the inputs start to increase, right at the beginning, our output increased till it reached the steady state, right? This feedback system is just giving us the difference between the desired value that we want to reach. Here is, for example, it's 25 something. So until we get the 25 output, this feedback gives the information to control system, so our input increase and we get the steady state and then it's stable. Right, this is how we use our feedback system, and we call this as a PID controller, and we're gonna see this in next semester or something. P controller, PI controller, and PID controller. So here now you can see this part here, your out is your input, and your feedback out input minus your feedback will give you error. It's your error here. So your desired value, it's 25 here. So till we get 25, we just increased our input value. So this is basic PI controller here. Okay, now let's take a look at the ramp input. Ramp input is just constantly accelerating input. All right. Okay, now your ramp input is not constant input, it's increasing constantly. Now you can change your slope to, let's make this to 52, and then apply it, and we can observe it again here. This is your orange one is your ramp input, and the blue one is your output, desired value. You increase your output, by the time your output also change with the feedback system. All right, any question till here, guys? Okay, let's go on to, okay, now let's take a look to our, what was it, root locus. Okay, determine to how we determine our roots of a transfer function. Okay, let's close this. Okay, now let's say we have a transfer function and we want to find the roots of this transfer function. In MATLAB, it's so easy to do it. It's just one line of code. Okay, let's say we have a first, you need to determine your numerator and denominator again, of course. Your denominator, let's add this one. Okay, now here you are gonna define your numerator and denominator, and then we're gonna use clue function. All right, open your parentheses, and inside you are gonna write your numerator and denominator again, and -1. So then you write your roots, parentheses, your denominator. All right, this function will find your roots of a system. Right, this is your roots, the real part and imaginary part of your roots. All right, any question? How we find the roots of a system? It's so easy on MATLAB, just like one line of code. All right, any question? Okay, assume you don't have it. All right. Okay, let's now take a look to how we get plot our poles and zeros. All right. Let's define our system first. First, we can define our system as like this. You don't need to write your denominator and denominator, or you can use this way. Your system equals transfer function. You can open parentheses inside here. You just need to define your numerator and denominator. all this, and then on your denominator. Okay. So when you define your system here, all you need to do it for the finding poles and zeros, just you write PZ map, pole zero map, and in the parentheses you write your system, right? And now it's gonna show us the map of the poles and zeros. Yeah, here. As you can see, you first define your system, and then with the P and Z map line of code, you just draw your poles and zero map. Here are your zeros and your poles. All right, any question, guys, still here? Okay, now today that was it for today's lab. Now I have a homework for you for the next week. I want everyone to pick a system, pick a system, and then find its transfer function, and then find the steady state, and then find the roots, and then I want you to plot the poles and zero map. All right, for the next week. Everyone just pick a system for themselves. All right. You can pick any system. You just define it. Find the transfer function. Find the steady state, and then find the roots, and then find the poles and zero map. All right. Okay, that was it for today, guys. See you next week. Have a nice day. Yeah, Hussein, yeah. Any question, guys? Hussein, you can ask. You can use your mic. Okay, you can rewatch the previous. It's already recorded.